So here's something that might seem a little strange to start with. You already understand thermodynamics, not in the textbook sense, not with the equations and the state variables and all that formalism, but in a deep, intuitive, bone-level way. You've understood it since you were a child. You knew that a hot cup of cocoa left on the counter would eventually get cold. You knew that you had to push harder to pedal your bike uphill. You knew, somehow, that you couldn't unscramble an egg. Nobody taught you those things explicitly. You just lived in a universe where they were true, and your brain quietly filed them away as the rules of the game. And that's really all thermodynamics is, when you strip away the Greek letters and the partial derivatives and the intimidating diagrams. It's the study of those rules, the rules about heat and energy and work, and why things change in the directions they do and never in reverse. It's the science of why things happen, not just how, not just when, but why this way and not that way, and the fact that those rules turn out to be so universal, so unbreakable, that Einstein himself once said that thermodynamics is the only physical theory of universal content that he was convinced would never be overthrown. Well, that tells you something about the kind of territory we're wandering into tonight. But let's not get ahead of ourselves. Let's go back, way back. Because the story of how humans figured out thermodynamics is one of the great intellectual adventures in history, and it starts, like so many things do, with fire. For most of human history, fire was basically magic. Useful magic, essential magic, but magic all the same. You burned wood and got heat. You burned coal and got more heat. Why? How? What was actually happening when something burned? Nobody really knew. And for thousands of years, nobody really needed to know. Fire worked. That was enough. Blacksmiths could forge iron without understanding combustion chemistry. Cooks could roast meat without a theory of heat transfer. The practical knowledge was there, passed down through apprenticeships and tradition, and it served people perfectly well. But then something changed. Sometime in the late 1600s and into the 1700s, people in Europe, particularly in Britain, started getting very, very interested in a specific practical question. Not what is fire in some abstract philosophical sense, but something much more concrete. They wanted to know how to pump water out of mines. Now, that might sound mundane, but think about what was happening in Britain at that time. The country was running on coal. Coal heated homes, coal powered early industries, and the demand for it was growing fast. But here's the problem. The deeper you dig a mine, the more groundwater seeps in. And if you can't get the water out, you can't get the coal out. And if you can't get the coal out, everything grinds to a halt. So mine drainage wasn't just an engineering nuisance, it was an economic crisis in slow motion. For a while, they used horses. Teams of horses walking in circles, turning pumps, lifting water bucket by bucket. It worked, sort of, but it was expensive, slow, and the horses had an annoying habit of needing food and rest. What people really wanted was a machine, something that could pump water tirelessly, day and night, without eating oats. And this is where a guy named Thomas Savery enters the picture. Savery was an English military engineer, an inventor, a tinkerer, the kind of person who was always fiddling with something. Around 1698, he patented a device he called the miner's friend. The basic idea was clever. You'd heat water in a sealed vessel until it turned to steam, filling the chamber. Then you'd cool the chamber down by pouring cold water over it. The steam would condense back into liquid water, and since liquid water takes up vastly less space than steam, we're talking something like 1,600 times less volume, that condensation would create a partial vacuum inside the chamber, and that vacuum would suck water up from the mine below. Think about that for a second. Savory was using the atmosphere itself as his muscle, the weight of all that air above us, pressing down on everything, about 14.5 pounds on every square inch. That air pressure would push water up into the vacuum that the condensing steam left behind. It's a beautiful idea. Nature abhors a vacuum, as the old saying goes, and Savory figured out how to make nature do useful work because of it. But here's the thing. Savory's engine had serious problems. The vacuum could only lift water about 30 feet or so, because that's the limit of what atmospheric pressure can support. A column of water, about 33 feet tall, give or take. Mines were often much deeper than that. So Savory tried using pressurized steam to push water the rest of the way up. But the boilers and vessels of his era couldn't handle high pressures safely. They leaked. They burst. The soldered joints failed. It was dangerous, and it was unreliable. And while Savory deserves credit for the concept, his engine never really solved the mine drainage problem at scale. The person who did solve it, or at least got a lot closer, was Thomas Newcomen. Newcomen was a different kind of character. He wasn't a gentleman inventor or a military engineer. He was an ironmonger from Dartmouth, a hardware dealer who sold tools to the mining industry. He knew miners. He knew their problems. And sometime around 1712, after years of quiet development, he built an engine that actually worked. Newcomen's engine used the same basic principle as Savory's: steam, condensation, vacuum, but with a crucial mechanical improvement. Instead of using the vacuum directly to suck up water, Newcomen used it to drive a piston inside a cylinder. The steam would fill the cylinder, pushing the piston up. Then a jet of cold water would spray into the cylinder, condensing the steam and creating a vacuum below the piston. The atmosphere would then push the piston back down, and that piston was connected through a big rocking beam to a pump down in the mine, up, down, up, down. About 12 strokes a minute, slow and ponderous, the great beam rocking back and forth like a giant breathing. It was loud. It was inefficient. It consumed enormous quantities of coal. But it worked. It actually, reliably, continuously pumped water out of mines. And because the mines had coal right there, you were literally sitting on top of the fuel supply. The inefficiency didn't matter as much as you might think. What mattered was that the water came out and the miners could keep digging. Newcomen engines spread across Britain and then across Europe. By the middle of the 1700s, there were hundreds of them, nodding away at mine heads, and they became one of the defining technologies of the early industrial age. But here's what's fascinating from our perspective. Nobody who built or operated these engines really understood why they worked. I mean, they understood the mechanics. Steam goes in, cold water condenses it, piston goes down. But the deeper questions: what is heat, actually? What's happening to the energy when steam condenses? Why does it take so much coal to do so little useful work? Those questions were still wide open. And this is the beautiful tension at the heart of early thermodynamics. The practice was ahead of the theory. The machines existed before the science that explained them. People were harnessing the power of heat and steam through trial and error, through intuition and craftsmanship, and the theoretical framework was scrambling to catch up. Now, to understand why the theory was so slow in coming, you need to appreciate just how confused people were about heat itself. And I mean genuinely, deeply confused. Today we take it for granted that heat is a form of energy, that it's related to the motion of atoms and molecules, that temperature measures the average kinetic energy of those tiny particles. But in the 1700s, none of that was established. Atoms were still a speculative idea. The dominant theory of heat was something called caloric theory, and it held that heat was an actual physical substance, a weightless, invisible fluid called caloric that flowed from hot objects to cold ones. And honestly, if you think about it, caloric theory isn't a crazy idea. It really does seem like heat flows. You put a hot iron next to a cold one, and the hot one cools down while the cold one warms up, as if something is literally pouring from one to the other. You can even do experiments that seem to support it. The French chemist Antoine Lavoisier, the same Lavoisier who figured out what oxygen was, and who lost his head to the guillotine during the French Revolution. Lavoisier was a big proponent of caloric theory. He thought caloric was a real element, as real as oxygen or hydrogen, just harder to detect because it was weightless. The caloric theory could explain a lot of everyday observations pretty well. Heat flows downhill, from hot to cold, just like water flows downhill from high to low. When you compress a gas, it gets hotter. Well, maybe you're squeezing the caloric out of it. When you mix hot and cold water, you get warm water. The caloric is just distributing itself evenly. It all seemed to hang together, but there were cracks. There were observations that didn't quite fit, and one of the most famous came from a truly unlikely source, an American-born British loyalist, adventurer, spy, and self-promoter named Benjamin Thompson, who later became Count Rumford. Thompson had one of the most colorful lives of the 18th century. Born in Massachusetts, he spied for the British during the American Revolution, fled to England, was knighted, moved to Bavaria, reorganized the Bavarian army, invented a more efficient fireplace, founded the Royal Institution in London, and somehow, in between all of that, made a crucial observation about the nature of heat. It happened in Munich, around 1798. Thompson was overseeing the boring of brass cannons at the military arsenal, boring as in drilling out the barrel, a process that generated enormous amounts of heat through friction. The brass shavings were hot, the cannon was hot, everything was hot, and they had to keep pouring water over the whole apparatus to keep it cool. Now, under caloric theory, this heat was supposed to be caloric fluid being squeezed out of the brass as it was cut and ground away. But Thompson noticed something that didn't add up. The heat just kept coming. As long as the boring tool kept turning, heat kept being produced. It didn't matter how much brass had been removed. Even a dull tool, one that was barely cutting any metal at all, produced enormous amounts of heat. If caloric were a substance contained in the brass, you'd expect it to run out eventually, like squeezing water from a sponge. But it never ran out. The supply of heat seemed inexhaustible, as long as you kept doing mechanical work. Thompson concluded that heat could not be a material substance. It had to be something else, something related to motion. He wrote it up and published it, and his paper is one of those landmark documents in the history of science. He was right, fundamentally right, that heat is related to motion rather than being a fluid. But here's the thing. Almost nobody listened, not right away. Caloric theory was too entrenched, too useful, too elegant in its own way, and Thompson himself, brilliant as he was, didn't provide a complete alternative theory. He poked a hole in the old idea without fully building the new one. So as the 1700s turned into the 1800s, the situation was this. There were these incredible machines, steam engines, transforming the world, pumping water, and soon they'd be driving factories and locomotives and ships. And there was this deep, unresolved question about what heat actually was and how it related to mechanical work. The practical engineers kept building bigger and better engines. The natural philosophers kept arguing about caloric. And somewhere in the gap between those two worlds, the science of thermodynamics was waiting to be born. The person who would take the first truly decisive step toward that science was, improbably, a young French military engineer who published one slim book, was largely ignored during his lifetime, and died of cholera at the age of 36. His name was Sadi Carnot, and his father was one of the most powerful men in Napoleonic France, and the question that consumed him was deceptively simple. He wanted to know, is there a limit to how efficient a steam engine can be? Is there some theoretical maximum, some ceiling that no amount of clever engineering can ever break through? And the answer he found would change everything, not just for steam engines, but for our entire understanding of the physical universe. Sadi Carnot was born in 1796, right in the thick of revolutionary France. His father, Lazare Carnot, was a mathematician, a military strategist, and a political figure of enormous influence. The man sometimes called the organizer of victory for his role in directing the French revolutionary armies. So young Sadi grew up in a household where intellectual rigor and strategic thinking were just the air you breathed, attended the École Polytechnique in Paris, which was essentially the most elite technical school in the world at that time, and then he went on to military engineering training. But here's the thing about Carnot. By the time he was in his mid-20s, he found himself on half pay, essentially sidelined from active military duty because of the political upheavals following Napoleon's fall. And instead of languishing, he threw himself into the question that fascinated him most. He looked across the English Channel and saw Britain pulling ahead of France economically, and he understood that a huge part of that advantage came down to one technology, the steam engine. British engineers, people like James Watt, who we'll get to, had refined the steam engine into something genuinely powerful and relatively reliable. France was behind, and Carnot, with his engineer's mind and his mathematician's instincts, didn't just want to build a better engine. He wanted to understand, at the deepest possible level, what governed how much useful work you could extract from heat, not for any particular engine, but for any engine, ever. So in 1824, when he was just 28 years old, he published a book called Reflections on the Motive Power of Fire. And this book, this slim, unassuming little volume, is one of the most remarkable documents in the history of science. It's beautifully written, actually. Clear, logical, almost conversational in places. And what Carnot does in it is something no one had done before. He abstracts away from the messy details of any specific engine, the pistons, the boilers, the condensers, the particular fuel, and asks a pure question. He imagines an idealized engine, a perfect engine with no friction, no heat leaking where it shouldn't, no wasted motion. And he asks, even for this perfect engine, is there a maximum efficiency? Can you ever convert all the heat into work? Now, here's what's fascinating and a little ironic. Carnot actually used caloric theory to develop his arguments. Remember caloric? That imaginary fluid of heat that Lavoisier championed and that Rumford had poked holes in? Carnot worked within that framework. He imagined heat as a substance flowing from a hot body to a cold body, like water flowing downhill. And he reasoned by analogy with water wheels. Think about a water wheel for a second. The amount of work you can get from a water wheel depends on two things: the amount of water flowing and the height it falls. A water wheel where water drops 10 feet does more work than one where water drops 2 feet. All else being equal. Carnot applied the same logic to heat engines. He said the motive power of a heat engine depends on the amount of heat flowing and the temperature difference it flows across. Heat falling from a high temperature to a low temperature is like water falling from a height. That's where the work comes from. And then he arrived at his crucial insight. He showed that the efficiency of an ideal engine depends only on the temperatures of the hot source and the cold sink. That's it. Not on the working substance. Not on whether you use steam or air or anything else. Not on the mechanical details, just the temperatures. And no real engine can ever be more efficient than this ideal engine operating between those same two temperatures. That's a ceiling. A hard, absolute, unbreakable ceiling. Let that sink in for a moment, because it's genuinely profound. What Carnot is saying is that the universe itself imposes a limit on how well you can convert heat into work. You can be clever. You can be brilliantly inventive. You can minimize every source of friction and waste. But you will never, ever exceed the Carnot efficiency. It's not an engineering limitation. It's a law of nature. And here's the kicker. The only way to reach 100% efficiency would be to have your cold reservoir at absolute zero, the lowest temperature theoretically possible. Since that's unattainable, perfect efficiency is impossible. Every real heat engine must waste some energy. Some heat must always flow to the cold side without doing work. Always. It's not that we haven't been clever enough. It's that the universe won't allow it. Now, Carnot published this, and you might expect it to have caused a sensation. It didn't. The book sold poorly. Most physicists and engineers didn't read it. Carnot was not a famous figure. He was a young, semi-retired military engineer without a prestigious academic position, and the book's arguments, while brilliant, were embedded in caloric theory, which made some natural philosophers uneasy even as others still clung to it. So, the work sat there, mostly unread, for over a decade. And then Carnot died. In 1832, during a cholera epidemic in Paris, he contracted the disease and was gone at 36. Most of his papers were burned, as was standard practice at the time to prevent the spread of infection. Think about that. We lost almost everything this man ever wrote. What survived was the published book and a few scattered notes. And in those surviving notes, there are tantalizing hints that Carnot, before he died, had actually abandoned caloric theory. He'd come around to something very close to the idea that heat is a form of motion, that it's convertible to work, and vice versa. He may have even estimated what we now call the mechanical equivalent of heat, the precise conversion factor between thermal energy and mechanical energy. But none of that was published. It was lost to cholera and fire. So the story of thermodynamics has this bittersweet quality right at its origin. The foundational insight was there, in that 1824 book, but the world wasn't ready for it. And the person who might have pushed the science forward by decades was gone before he could. The person who rescued Carnot's work from obscurity was a French engineer and physicist named Émile Clapeyron. In 1834, Clapeyron published a paper that restated Carnot's ideas in more rigorous mathematical language, with elegant diagrams, including what we now call the Carnot cycle, shown as a loop on a pressure-volume diagram. Clapeyron made Carnot's arguments accessible to the broader scientific community. And it was through Clapeyron's paper that Carnot's ideas eventually reached the two men who would build the formal edifice of thermodynamics: William Thomson, who became Lord Kelvin, and Rudolf Clausius. But before we get to them, we need to talk about what was happening on a parallel track, because thermodynamics didn't come from just one direction. While Carnot was thinking about engine efficiency in France, other people in other places were circling around a different but deeply related question. What exactly is the relationship between heat and mechanical work? Can you measure it? Can you put a number on it? This is where we meet James Prescott Joule, and his story is one of my favorites in all of science because he was not a professional scientist. He was a brewer. His family owned a brewery in Salford, near Manchester, England, and Joule became obsessed, truly obsessed, with measuring things precisely. He wanted to know exactly how much mechanical work it took to raise the temperature of water by 1 degree. Think about what that question means. If heat is truly a form of energy, then there should be a fixed, universal conversion rate. 1 unit of mechanical work should always produce the same amount of heat, no matter how you do it. Joule set out to prove this, and he did it through a series of experiments that are almost comically painstaking. The most famous one involved a falling weight connected by a string and pulley to a paddle wheel, submerged in an insulated container of water. The weight falls, the paddle turns, the water gets stirred, and the friction of the stirring heats the water. Joule measured the distance the weight fell and the tiny temperature increase in the water with extraordinary precision. We're talking fractions of a degree Fahrenheit. He did this over and over and over. He tried different methods too, squeezing air, forcing water through narrow tubes, even using electrical currents. And every method gave him essentially the same conversion factor. A specific amount of mechanical work always produced the same amount of heat. He first presented his results in 1843, and again, more definitively, in 1845 and 1847. And like Carnot before him, he was largely ignored at first. The scientific establishment was skeptical. Here was this brewer from Manchester, not a university man, claiming to have established a fundamental law of nature with homemade apparatus. When he presented his paddle wheel results at a meeting of the British Association for the Advancement of Science in 1847, the chairman reportedly suggested he give just a brief verbal summary so they could move on to other business. But someone in that audience was paying attention. A young man, just 23 years old, named William Thomson, the future Lord Kelvin. Thomson was intrigued by Joule's results, partly because he'd recently been reading Clapeyron's paper on Carnot's work, and he could sense that these two threads, Carnot's theoretical limit on engine efficiency and Joule's experimental proof that heat and work are interconvertible, were connected, but they also seemed to contradict each other in a troubling way. Carnot's analysis, at least as it was framed in caloric theory, assumed that heat was conserved, that it flowed through the engine like water through a water wheel, doing work but not being used up. Joule's experiments showed that heat could be created from work and, by implication, destroyed, converted entirely into work. Both couldn't be right, or could they? This tension, this apparent contradiction between Carnot and Joule, is exactly where thermodynamics was about to crack open, and the person who would resolve it, who would see how both men could be essentially correct while caloric theory was wrong, was working in Germany, thinking very carefully about what it really means when heat flows from hot to cold. His name was Rudolf Clausius, and he was about to introduce an idea so subtle and so powerful that we're still wrestling with it today. Rudolf Clausius, born in 1822 in Köslin, a small town in what was then the Prussian province of Pomerania. He was the son of a pastor and school principal, one of many children in a large family, and from early on he showed that particular kind of mind that could hold multiple ideas in tension without flinching. He studied at the University of Berlin, worked under some of the best physicists in Germany, and by his late 20s, he was quietly assembling a picture of heat and energy that would reshape everything. Here's what Clausius did in 1850, and it's one of those moves in the history of science that looks almost surgical in hindsight. He published a paper. Its title translates roughly as On the Moving Force of Heat and the Laws Which May Be Deduced Therefrom. And in it, he essentially said, Carnot was right about the efficiency limit. Joule was right about the interconvertibility of heat and work. And caloric theory is wrong. All three of those things can be true at the same time, and here's how. The key insight was this. Carnot had shown that you can't convert heat into work without having a temperature difference. You need a hot source and a cold sink, and the efficiency depends on that temperature gap. That part was correct, and didn't actually require caloric theory at all. What caloric theory added, unnecessarily, was the claim that the total amount of heat was conserved, that the heat flowing into the engine equaled the heat flowing out, like water through a mill. Clausius said no. Some of the heat that flows in from the hot source is genuinely converted into work. It doesn't come out the other side. The heat that does come out at the cold end is less than what went in, and the difference is exactly the work the engine performed. So Carnot's limit still holds. You still can't beat that maximum efficiency set by the temperatures, but the reason isn't that heat is a conserved fluid. The reason is something deeper, something about the fundamental directionality of how heat moves in the universe. Think about what that means. Clausius kept the baby and threw out the bathwater, if you'll forgive the expression. He preserved Carnot's most important result while replacing the underlying theory with something that was consistent with Joule's experiments. And in doing so, he essentially stated what we now call the first law of thermodynamics in a clear, general form. Energy is conserved. It can change forms. Heat can become work. Work can become heat. But the total amount of energy in a closed system stays the same. That's it. That's the first law. It sounds almost too simple, doesn't it? But getting to that simple statement required decades of confusion, argument, and painstaking experiment. Now, William Thomson over in Glasgow was working on very similar ideas at almost exactly the same time, and there's a bit of a priority question here that historians have debated. Thomson had been wrestling with the Carnot-Joule contradiction since that 1847 meeting, and by 1851, he published his own paper laying out what he called the dynamical theory of heat. His formulation was independent of Clausius's, and in some ways it was more physically intuitive. Thomson emphasized something that Clausius had also noticed, but hadn't yet made the centerpiece of his thinking. The idea that there's a directionality to heat flow. Heat naturally flows from hot to cold, never the other way around, without some external work being done. You know this intuitively. Your coffee cools down. It never spontaneously heats up by absorbing energy from the cooler air around it. A warm room doesn't suddenly develop a hot spot in one corner and a cold spot in another, even though that wouldn't violate conservation of energy. Something else is going on, some other principle beyond just energy bookkeeping. And this is where the second law of thermodynamics enters the picture, and honestly, this is where thermodynamics goes from being a useful engineering tool to being something almost philosophical. The first law tells you what's possible in terms of energy accounting. The second law tells you what's possible in terms of direction. It tells you which way processes actually go. And it's one of those ideas that seems straightforward when you first hear it, but gets more and more profound the longer you sit with it. Clausius stated it one way: heat cannot, of itself, pass from a colder body to a warmer one. Thomson stated it differently: it is impossible to construct a device that operates in a cycle and produces no effect other than the extraction of heat from a single reservoir and the performance of an equivalent amount of work. These sound like they're saying different things, but they're actually equivalent. You can prove that if one is violated, the other must be too. They're two faces of the same deep truth about the universe. Let's unpack Thomson's version for a second, because it's really clever, and it connects directly back to engines. What he's saying is, you cannot build a perfect engine. You cannot take heat from a single source, say, the ocean, which contains an enormous amount of thermal energy, and convert all of it into useful work with nothing left over. There must always be some waste heat dumped into a cooler reservoir, always. Not because of friction, not because of engineering limitations, but because of a fundamental law of nature. Even Carnot's ideal engine, the most perfect engine conceivable, still has to reject some heat to the cold sink. The only way to get 100% efficiency would be to have a cold reservoir at absolute zero, which is itself impossible to reach. So there's this inescapable tax that nature imposes on every energy conversion process. You can never break even. You always lose something. Here's the thing that makes this so fascinating. The first law says you can't create energy from nothing. You can't win. The second law says you can't even break even. Every conversion has a cost. Together, they paint a picture of a universe where energy is conserved, but its usefulness is constantly degrading. And that word, usefulness, is doing a lot of heavy lifting there, because it points towards something Clausius was going to spend the next 15 years trying to quantify. But let me step back and tell you a little more about these two men, Clausius and Thomson, because their parallel work on the second law is one of those fascinating episodes where two brilliant minds are circling the same truth from different directions. Thomson, Lord Kelvin, as he'd later become, was in many ways the more publicly prominent figure. He was charismatic, well-connected, a professor at the University of Glasgow at the absurdly young age of 22. He would go on to have an extraordinary career. He was instrumental in laying the first transatlantic telegraph cable. He developed the absolute temperature scale that bears his name. He became one of the most celebrated scientists in the British Empire. He was knighted, then raised to the peerage. When he died in 1907, he was buried in Westminster Abbey next to Isaac Newton. Clausius, by contrast, was quieter, more methodical, less flashy. He spent most of his career at various German and Swiss universities, and while he was respected, he never achieved the kind of public fame that Thomson enjoyed. But in terms of the actual theoretical development of thermodynamics, Clausius arguably went deeper. He was the one who kept pushing, kept asking, what exactly is this quantity that determines the direction of natural processes? What is the mathematical thing that always increases? And this is where we get to entropy, which is probably the most misunderstood and most important concept in all of thermodynamics. Clausius didn't arrive at it all at once. It took him from 1850 to 1865, 15 years of careful thinking and refinement, to fully articulate what he meant. In those early papers, he talked about what he called the equivalence value of transformations, a clunky phrase that he knew wasn't quite right. He was trying to capture the idea that when heat flows from hot to cold, or when work is converted to heat, there's a kind of transformation happening, and these transformations have a natural direction. They accumulate, and the mathematical quantity that tracks this accumulation needed a name. In 1865, Clausius coined the word entropy, deliberately choosing a Greek root, trope, meaning transformation or turning, to echo the word energy. He wanted the two concepts to feel like siblings, which in a sense they are. Energy tells you how much, entropy tells you which way. And he summarized the two laws of thermodynamics in what might be the most elegant pair of sentences in all of physics. The energy of the universe is constant. The entropy of the universe tends toward a maximum. Let that sink in for a moment. The energy of the universe is constant. Nothing is being created or destroyed, just shuffled around, converted from one form to another. But the entropy, this measure of transformation, of dispersal, of things spreading out and evening out, that only goes up. It's like a one-way ratchet built into the fabric of reality. Now, what does entropy actually mean in physical terms? This is where people get confused, and honestly, it's where a lot of textbooks do a poor job. You'll often hear entropy described as disorder, and while that's not completely wrong, it's misleading enough to cause real problems. Let me try a different approach. Think about entropy as a measure of energy dispersal. How spread out the energy in a system is among all the possible ways it could be arranged. When energy is concentrated, like in a hot object sitting in a cold room, that's a low entropy state. There's a big temperature difference, and that difference represents a potential to do work, to drive a process. As the hot object cools down and the room warms up slightly, the energy spreads out more evenly. The temperature difference shrinks, the entropy increases, and when everything reaches the same temperature, the entropy is at its maximum for that system, and no more work can be extracted. The energy is still there. First law, remember, it's conserved. But it's useless now. It's spread out so evenly that there's no gradient, no difference to exploit. Think of it like water. If you have a lake on top of a mountain and a valley below, the height difference means the water can flow downhill and turn a turbine on the way. That's useful energy. But once the water reaches the valley and spreads out into a flat, still pond, the energy of its elevated position is gone. The water molecules are still there. They still have mass. But you can't extract any more work from the height difference, because there is no height difference anymore. Entropy is like the measure of how much of that leveling out has happened. And here's what's really beautiful about Clausius's formulation. He showed that for any reversible process, any idealized, perfectly efficient process like Carnot's ideal engine, the total entropy change is zero. Nothing is gained, nothing is lost. But for any real process, any irreversible process, which is to say every actual process that happens in the real world, entropy increases, always, without exception. Friction generates entropy. Heat flowing across a temperature difference generates entropy. Mixing two gases generates entropy. Every real thing that happens pushes the universe's entropy a little higher. This is why Carnot's ideal engine was so important, even though it can never actually be built. It represents the boundary, the theoretical line between possible and impossible. Any real engine will produce more entropy than Carnot's ideal, which means it will be less efficient. You can approach Carnot's limit, get closer and closer with better engineering, but you can never reach it, and you can certainly never surpass it. Nature draws a line, and no amount of cleverness can cross it. Now, while Clausius and Thomson were working out these grand principles in the 1850s and 1860s, something else was happening that would eventually transform thermodynamics from the inside out. Over in Austria, a young physicist named Ludwig Boltzmann was growing up, and he was about to ask a question that sounds innocent but turns out to be explosive. If matter is made of atoms, tiny particles bouncing around according to the laws of mechanics, then what is heat really? What is temperature really? And what is this strange quantity called entropy in terms of what the atoms are actually doing? Because here's the thing that was nagging at people. Clausius and Thomson had built thermodynamics as a macroscopic theory. It dealt with bulk properties, temperature, pressure, volume, heat flow, without saying anything about what matter was made of at the microscopic level. You didn't need to believe in atoms to use thermodynamics. In fact, many prominent scientists in the late 19th century didn't believe in atoms. Ernst Mach, the influential Austrian physicist and philosopher, was openly hostile to the idea. He considered atoms a convenient fiction, a mental crutch that had no place in rigorous science, and he wasn't alone. Boltzmann disagreed, profoundly, and his attempt to ground thermodynamics in the mechanical behavior of atoms and molecules would lead to one of the most beautiful and most contested ideas in the history of physics. It would also, tragically, contribute to a personal crisis that would cast a long shadow over his life. Boltzmann was born in Vienna in 1844, right in the middle of that extraordinary period when Joule was nailing down the mechanical equivalent of heat and Clausius was about to resolve the Carnot-Joule tension. He grew up in a world where thermodynamics was being assembled in real time, and he came of age just as the first and second laws were settling into their mature forms. He studied physics at the University of Vienna, earned his doctorate at 22, and almost immediately began working on the kinetic theory of gases. The idea that a gas is just a vast swarm of tiny particles in constant chaotic motion, and that everything we observe about gases at the macroscopic level, their pressure, their temperature, their behavior when heated or compressed, emerges from the collective statistics of those particles. Now, the kinetic theory wasn't entirely new. Daniel Bernoulli had sketched out the basic idea way back in 1738, suggesting that gas pressure comes from particles smacking into the walls of a container. James Clerk Maxwell, the great Scottish physicist, had taken this much further in the 1860s, showing that the speeds of gas molecules follow a specific statistical distribution, what we now call the Maxwell distribution. Not all molecules in a gas move at the same speed. Some are crawling, some are zipping along at tremendous velocity, and most are somewhere in the middle. Maxwell worked out the exact mathematical shape of this distribution, and it matched experimental observations beautifully. So the kinetic picture was gaining traction. But here's where Boltzmann enters and pushes everything further than anyone had dared. What Boltzmann wanted to do was take entropy, that mysterious, somewhat abstract quantity Clausius had defined, and explain it in terms of atoms. Not just describe it macroscopically, not just say entropy increases, but explain why it increases by looking at what the atoms are doing. And the answer he arrived at, after years of painstaking work through the 1870s and into the 1880s, is one of the most elegant ideas in all of science. Let me try to explain it the way he saw it. Imagine you have a box, and inside that box is a gas. Let's say a few trillion molecules of air, bouncing around, colliding with each other and with the walls. At any given instant, each molecule has a specific position and a specific velocity. If you could somehow freeze time and write down the exact position and velocity of every single molecule, you'd have what physicists call a microstate, a complete, exhaustive description of the system at the atomic level. Now, You can never actually do this. There are far too many particles. But conceptually, the microstate is perfectly well defined. It's the full microscopic truth of the system at one moment. Here's the key insight. When you measure something macroscopic, like the temperature of the gas, or its pressure, or its volume, you're not measuring the microstate. You're measuring what's called a macrostate. A macrostate is defined by those bulk properties: temperature, pressure, volume, energy. And here's what's really clever about Boltzmann's thinking. Many different microstates can correspond to the same macrostate. Think about it. If the gas has a certain temperature and pressure, there are trillions upon trillions of different ways the individual molecules could be arranged. Different positions, different velocities, that would all give you the same temperature and pressure when you measure them. The macroscopic properties don't change if you swap two molecules, or if one molecule speeds up slightly, while another slows down by the same amount. All of those rearrangements are different microstates, but they look the same from the outside. So Boltzmann defined a quantity, call it W, that counts the number of microstates corresponding to a given macrostate. And then he made his great claim: entropy is proportional to the logarithm of W. More microstates means higher entropy. Fewer microstates means lower entropy. That's it. That's the whole idea at its core. S equals K log W, where S is entropy, K is a constant, now called Boltzmann's constant, and W is the number of microstates. This equation is so important that it's literally carved on Boltzmann's tombstone in Vienna. If you ever visit the Zentralfriedhof, the great central cemetery there, you can see it. Now let's unpack why this is so powerful, because it does something remarkable. It explains the second law of thermodynamics. Entropy always increases, not as some mysterious cosmic decree, but as pure statistics. Think about it this way. If a system can be in any microstate with roughly equal probability, and this is a key assumption, but a reasonable one for systems in equilibrium, then the system is overwhelmingly more likely to be found in a macrostate that corresponds to a huge number of microstates than in one that corresponds to a tiny number. And the macrostates with the most microstates are the ones with the highest entropy. So the system naturally evolves toward higher entropy simply because there are vastly more ways to be in a high entropy state than a low entropy one. It's not that the system is forbidden from decreasing its entropy. It's that the probability of a significant, spontaneous decrease is so astronomically small that you'd have to wait longer than the age of the universe to see it happen. Let me give you an analogy. Imagine you have a deck of cards, perfectly sorted. All the hearts in order, then all the diamonds, then clubs, then spades. That's a very low entropy state. There's essentially one arrangement that looks like that. Now shuffle the deck. After one shuffle, it's probably a little disordered. After 10 shuffles, it's thoroughly mixed. The mixed state has enormously higher entropy because there are billions of possible arrangements that look random, and only one that looks perfectly sorted. If you keep shuffling, will the deck ever return to perfect order? In principle, yes. It's not impossible. But the number of shuffles you'd need on average is so staggeringly large that it's effectively never going to happen. That's the second law, according to Boltzmann. It's not a law of impossibility. It's a law of overwhelming probability. And this is where the trouble started. Because the moment Boltzmann framed the second law as statistical rather than absolute, he ran into fierce opposition from multiple directions. The first objection came from people like Mach and the energeticists, Wilhelm Ostwald being another prominent figure, who simply didn't accept atoms. If you don't believe atoms exist, then the entire foundation of Boltzmann's argument collapses. You can't count microstates of particles you don't think are real. Mach was particularly cutting. He was a towering intellectual figure, a philosopher-physicist whose ideas about the nature of scientific knowledge would later influence Einstein. And Mach's position was that science should deal only with observable quantities. Atoms were not observable. Therefore, atoms were metaphysics, not physics. Boltzmann's statistical mechanics was, in Mach's view, building an elaborate theoretical castle on imaginary foundations. The second objection was more technical and came from within the physics community itself. It's called the reversibility paradox, and it was raised most sharply by Joseph Loschmidt, who was actually Boltzmann's friend and colleague in Vienna. Here's the problem. The laws of mechanics, Newton's laws, the equations governing how particles move and collide, are time reversible. If you filmed a bunch of billiard balls colliding and then played the film backward, the reversed motion would also obey Newton's laws perfectly. There's nothing in the microscopic equations that distinguishes past from future. Every collision can happen in reverse. So how can you derive an irreversible law? Entropy always increases. Time has a direction. From reversible microscopic physics. It seems like a contradiction. You're trying to get a one-way arrow out of equations that work equally well in both directions. This bothered Boltzmann deeply, and he spent years refining his arguments to address it. His response was subtle and, honestly, ahead of its time. He argued that the second law is not a mechanical law, but a statistical one. The microscopic equations are indeed reversible. Any individual trajectory can be reversed. But when you're dealing with astronomical numbers of particles, and remember, a single breath of air contains something like 10 to the 22nd power molecules, the statistics become so overwhelmingly one-sided that the probability of observing a macroscopic decrease in entropy is effectively zero. The reversibility paradox isn't really a paradox, Boltzmann insisted. It just shows that the second law has a different character than Newton's laws. It's not about what must happen. It's about what almost certainly will happen. And for any system with a realistic number of particles, almost certainly is so close to certainly that you could never tell the difference. There was a third objection too, called the recurrence paradox, raised by Ernst Zermelo, based on a theorem by Henri Poincaré. Poincaré had proved that any mechanical system confined to a finite region of space will, if you wait long enough, return arbitrarily close to its initial state. So if you start with low entropy and the system evolves to high entropy, eventually, given enough time, it should return to low entropy. Doesn't that violate the second law? Boltzmann's answer was essentially, yes, Poincaré recurrence is real, but the timescales involved are so incomprehensibly vast, far longer than the age of the universe, that they have no practical relevance whatsoever. The second law holds for any timescale that any observer could ever actually experience. These debates raged through the 1890s, and they took a real toll on Boltzmann. He was a passionate, emotional man, large in stature, generous with students, prone to self-doubt. He described himself as being in constant battle. The opposition wasn't just intellectual, it felt personal. Mach's criticism carried enormous institutional weight. Ostwald's energetics program was gaining followers, and Boltzmann sometimes felt that the entire physics establishment was turning against the atomic hypothesis, against his life's work. He suffered from what we would now recognize as severe depression, with episodes that worsened over the years. In 1906, while on vacation with his family in Duino, near Trieste, Ludwig Boltzmann took his own life. He was 62 years old. It's one of the most heartbreaking stories in the history of science, because within just a few years of his death, the tide turned completely. Einstein's 1905 paper on Brownian motion provided compelling theoretical evidence for atoms. Jean Perrin's experiments in the years that followed confirmed Einstein's predictions quantitatively. By 1910, even Ostwald had conceded that atoms were real. Boltzmann had been right all along. He just didn't live to see it. And here's what makes it even more poignant. That equation on his tombstone, S equals K log W, didn't just survive the controversy. It became one of the cornerstones of modern physics. It connects the microscopic world to the macroscopic world. It tells you that entropy isn't some mysterious fluid or abstract bookkeeping device. It's a measure of how many ways the microscopic pieces of a system can be rearranged without changing what you see from the outside. High entropy means lots of possible arrangements. Low entropy means few, and nature, left to itself, moves from few to many, from ordered to disordered, from special to typical, simply because typical arrangements are overwhelmingly more numerous. Now, I want to sit with that idea for a moment, because it reshapes how you think about the second law in everyday life. When you leave a hot cup of coffee on the counter and it cools down, the heat energy from the coffee is spreading out into the surrounding air. The energy isn't being destroyed, first law, conservation, but it's being dispersed among a vastly larger number of air molecules. The number of microstates available to the system increases enormously as the energy spreads. That's entropy increasing. And the reverse process, all those air molecules spontaneously conspiring to dump their energy back into the coffee and reheat it, would require an astronomically specific coordination of molecular motions. It's not forbidden by any law of mechanics. Every individual molecular collision involved in reheating the coffee is perfectly allowed by Newton's laws. But the probability of all of them happening in just the right way, at just the right time, is so vanishingly small that it might as well be zero. That's the second law, Boltzmann style. And this statistical understanding opens up something else, something that would become increasingly important in the 20th century. If entropy is about counting microstates, then entropy is fundamentally about information, about what you know and what you don't know about a system. If you know the exact microstate, every particle's position and velocity, then in a sense, the entropy is zero for you, because there's only one arrangement consistent with your knowledge. But if you only know the macroscopic properties, the entropy reflects your ignorance of the microscopic details. This connection between entropy and information would eventually be made rigorous by Claude Shannon in 1948, when he developed information theory and found that the mathematical formula for information entropy is essentially identical to Boltzmann's formula. That's a thread we'll come back to. But for now, what matters is that Boltzmann had cracked open something far deeper than he probably realized. He'd shown that the second law of thermodynamics is, at its heart, a statement about probability and information, not about energy or heat in isolation. So, by the early 20th century, thermodynamics had three pillars firmly in place. The first law, energy is conserved, you can't create or destroy it. The second law, entropy of an isolated system never decreases, and in practice, always increases. And Boltzmann's statistical interpretation, which explained why the second law works the way it does. But there was still one more law waiting to be formalized, and it concerned something that Carnot had actually hinted at decades earlier: the nature of absolute zero. What happens when you try to cool something down to the lowest possible temperature? Is there a lowest possible temperature? And what does entropy do as you approach it? A German chemist named Walther Nernst was about to wrestle with exactly these questions, and what he found would become the third law of thermodynamics, the final pillar, and in some ways the strangest one. Nernst is a fascinating character. Born in 1864 in Briesen, West Prussia, which is now part of Poland, he was one of those scientists who was brilliant, ambitious, and almost comically confident. He had a sharp mind and an even sharper tongue. Colleagues described him as short, round, energetic, and absolutely certain he was the smartest person in any room he walked into, which, to be fair, he often was. He studied under some of the great names in physics and chemistry, bounced between universities, and by the turn of the 20th century had landed at the University of Berlin, where he built one of the most productive physical chemistry laboratories in the world. Now, Nernst's main obsession wasn't thermodynamics in the abstract. He was a practical man. He wanted to be able to predict chemical reactions. Specifically, he wanted to know whether a given reaction would happen spontaneously or not. And this is where thermodynamics comes in, because the answer to that question depends on something called the free energy of the system. You might have heard the term Gibbs free energy if you ever took a chemistry class. The idea, which Josiah Willard Gibbs had worked out in the 1870s, is that a chemical reaction will proceed spontaneously if it decreases the free energy of the system. Free energy combines two things you already know about: the total energy, which is the first law territory, and the entropy, which is second law territory. Specifically, the Gibbs free energy equals the enthalpy minus the temperature times the entropy. Don't worry about memorizing that. The point is that to predict whether a reaction will go, you need to know both the energy change and the entropy change. Here's the problem Nernst ran into. By the early 1900s, chemists could measure energy changes in reactions pretty well. Calorimetry had gotten quite good. But entropy changes, those were much harder to pin down experimentally, especially at low temperatures. And the equations that connected everything had an annoying integration constant. Basically, an unknown number that you couldn't determine from the existing laws of thermodynamics alone. It was like having a perfectly good equation with one blank you couldn't fill in. The first and second laws together weren't enough to give you absolute values of entropy. They could tell you about changes in entropy, but not the starting point. So Nernst set out to solve this problem, and in 1906, the same year Boltzmann died, which is a poignant coincidence, he proposed what he called his heat theorem. The idea, stated simply, is this: as the temperature of a system approaches absolute zero, the entropy change associated with any process approaches zero. Let that sink in for a moment. He was saying that at the very bottom of the temperature scale, entropy differences between states vanish. Everything converges. Now, why would that be useful? Think about it this way. If you know that entropy changes go to zero at absolute zero, that gives you a fixed reference point. It's like having a sea level for entropy. Before Nernst, entropy was always relative. You could talk about how much entropy changed, but you couldn't say what the entropy actually was. Nernst's theorem effectively anchored the scale. Later, Max Planck extended this idea and proposed that the entropy of a perfect crystal at absolute zero is exactly zero. Not just that entropy changes vanish, but that entropy itself reaches zero. This is the version of the third law you'll find in most textbooks today. A perfect crystal at absolute zero has zero entropy because there's only one way to arrange it, one microstate. Remember Boltzmann's formula, S equals K log W. If W equals 1, one single microstate, then log of 1 is 0, and the entropy is 0. It fits together beautifully. But let's slow down and think about what absolute zero really means, because it's one of those concepts that sounds simple, but gets stranger the more you examine it. Absolute zero is 0 Kelvin, which is minus 273.15 degrees Celsius, or about minus 459.67 Fahrenheit. It's the temperature at which, classically speaking, all molecular motion would cease. Everything stops. No vibration, no rotation, no translation. Complete stillness. Now, quantum mechanics complicates this picture a bit. There's something called zero-point energy, which means particles retain a tiny residual energy even at absolute zero, because Heisenberg's uncertainty principle won't allow them to be perfectly still and perfectly located at the same time. But the classical picture gives you the right intuition. Absolute zero is the floor. You can't go below it. And here's what's really interesting about the third law in practice. It tells you that you can never actually reach absolute zero. This is sometimes stated as a separate formulation of the third law. No finite number of cooling steps can bring a system all the way to 0 Kelvin. You can get astonishingly close. Modern laboratories have cooled materials to within billionths of a degree of absolute zero. But you can't get there. Each successive step of cooling removes less and less entropy, and the closer you get, the harder it becomes. It's like an asymptote. You approach it forever, but never touch it. Think about what that means practically. Every refrigerator, every air conditioner, every cryogenic system in the world is fighting this battle. They're all trying to move heat from a cold place to a warm place, which the second law says doesn't happen spontaneously. You have to do work to make it happen. And the colder you want to go, the more work it takes per degree. The effort doesn't scale linearly. It gets exponentially harder as you approach absolute zero. This is why cryogenics is such a specialized and expensive field. Cooling a superconducting magnet for an MRI machine down to a few Kelvin above absolute zero requires liquid helium and elaborate insulation and pumps and a whole engineering infrastructure. And even then, you're still a few degrees above the floor. Nernst, by the way, didn't just contribute to pure science. He was also an inventor and entrepreneur. He developed the Nernst lamp, an early type of incandescent light that used a ceramic filament instead of a carbon one. It was more efficient than Edison's bulbs in some respects, and he sold the patent to the German company AEG for 1,000,000 marks, an enormous sum at the time. He used the money to buy a country estate and lived very comfortably. He also loved cars, owned several, and was one of the first people in Berlin to drive an automobile. There are stories of him tinkering with engines and once trying to use the waste heat from his car's exhaust to warm the interior. A very thermodynamic solution to a very practical problem. He won the Nobel Prize in Chemistry in 1920 for his heat theorem, though the award was actually for 1920, but presented in 1921 due to the committee's deliberations, and his life took darker turns after that. He lost 2 sons in the First World War, which devastated him. He continued working, but the rise of the Nazi regime in Germany was catastrophic for the scientific community he'd helped build. Many of his colleagues and students were Jewish, and Nernst, though not Jewish himself, was deeply opposed to the Nazis' persecution of scientists. He spoke out against it, which took courage, but also isolated him. He retired to his country estate and died in 1941, largely forgotten by the regime that had dismantled so much of German science. But his third law endured, and it completed the framework. So now you have the full set. The zeroth law, which we haven't really talked about yet, and it's worth a quick aside. The zeroth law is actually the simplest one, and it was formalized last, which is why it has that odd name. It was stated explicitly by Ralph Fowler in the 1930s, though the principle had been assumed implicitly for over a century. It simply says, if two systems are each in thermal equilibrium with a third system, then they're in thermal equilibrium with each other. That sounds almost trivially obvious, right? If object A is the same temperature as object C, and object B is the same temperature as object C, then A and B are the same temperature as each other. But this is actually the foundational statement that makes temperature a meaningful transitive property. Without it, the whole concept of temperature measurement falls apart. Every thermometer you've ever used relies on the zeroth law. The thermometer reaches equilibrium with your body, and then you read the thermometer, and you trust that the reading tells you something about your body's temperature. That chain of reasoning only works if thermal equilibrium is transitive, so they called it the zeroth law because it logically comes before the first, even though historically it was recognized after. So the full architecture of classical thermodynamics, as it stood by the mid-20th century, looks like this. The zeroth law gives you temperature. The first law gives you energy conservation. The second law gives you entropy and the arrow of time. The third law gives you the absolute reference point and the unattainability of absolute zero. And underneath all of it, Boltzmann's statistical mechanics explains why entropy behaves the way it does because of the overwhelming probability of high entropy states. Now, I want to take you somewhere that might seem like a detour, but it's really not. Because once you have this framework in place, once you understand energy, entropy, temperature, and absolute zero, you can start to see thermodynamics at work in places you might not expect. And one of the most dramatic arenas where thermodynamics shaped the modern world wasn't in a laboratory or a university lecture hall. It was in the development of engines. Not the old steam engines of Newcomen and Watt, but the internal combustion engines and the power plants and the refrigeration systems that defined the 20th century. Think about the engine in a car. What's actually happening in there? You're burning fuel, gasoline, which is a hydrocarbon, and the combustion releases energy as heat. That heat raises the temperature and pressure of the gases in the cylinder, which pushes a piston, which turns a crankshaft, which eventually turns the wheels. It's a heat engine, just like Carnot described. And Carnot's efficiency limit applies to it just as ruthlessly as it applied to the steam engines of the 1820s. The maximum efficiency depends on the temperature difference between the hot combustion gases and the cooler exhaust. A typical gasoline engine operates with combustion temperatures around 2,500 degrees Celsius and exhaust temperatures around 600 degrees Celsius, which gives a theoretical Carnot efficiency of maybe 60 or 70%. But real engines fall well short of that because of friction, heat losses through the engine block, incomplete combustion, and a dozen other practical imperfections. A typical car engine converts maybe 25 to 30% of the fuel's energy into useful work. The rest is waste heat. That's not a design flaw. It's thermodynamics. The second law sets a ceiling, and real-world engineering brings you somewhere below it. And this is where a German engineer named Nikolaus Otto and a French engineer named Etienne Lenoir and later Rudolf Diesel all enter the story. Because they were each trying to build better heat engines, and the differences between their approaches come down to thermodynamic cycles. specific sequences of compression, heating, expansion, and cooling that determine how efficiently the engine converts heat into work. Otto developed the four-stroke cycle that most gasoline engines still use today, patenting it in 1876. Diesel, who had actually studied thermodynamics under Carl von Linde in Munich, was obsessed with getting closer to Carnot's theoretical limit. He reasoned that if you could compress air to a much higher pressure before igniting the fuel, you'd get a higher temperature difference and therefore better efficiency. His diesel engine, which he patented in 1893 and demonstrated in 1897, did exactly that. And diesel engines remain more efficient than gasoline engines to this day, typically converting 35 to 45% of fuel energy into work. Diesel himself had a tragic end. He disappeared from a steamer crossing the English Channel in 1913, and his body was found days later. Whether it was suicide, murder, or an accident has never been definitively settled. Some historians lean toward suicide. Diesel was under enormous financial pressure at the time, and there's evidence he was nearly bankrupt despite the success of his engine. Others have speculated about foul play, noting that he was on his way to London to negotiate with the British Admiralty about fitting diesel engines to submarines, and that both German and British intelligence services might have had reasons to want those negotiations to fail. The truth is, we just don't know. What we do know is that the engine he left behind changed the world. Container ships, freight trains, heavy trucks, power generators, agricultural equipment, diesel engines are everywhere, quietly converting fuel into work at efficiencies that would have made Carnot nod with something like approval. But here's the thing about thermodynamic cycles, and this is worth sitting with for a moment. The differences between the Otto cycle and the diesel cycle aren't just engineering trivia. They're different strategies for navigating the same fundamental constraints. In the Otto cycle, you compress a fuel-air mixture and then ignite it all at once with a spark plug. That's roughly a constant volume combustion process. The fuel burns so fast that the piston barely moves during ignition, so the volume stays approximately the same, while the pressure and temperature spike. In the diesel cycle, you compress just air to a very high pressure and temperature, then inject fuel gradually, so it burns more slowly as the piston is already moving outward. That's closer to a constant pressure process. The pressure stays roughly steady, while the volume increases during combustion. And each of these idealized cycles has a different efficiency formula, a different relationship between compression ratio and thermal efficiency. The diesel cycle can use higher compression ratios because you're only compressing air, not a fuel-air mixture that might detonate prematurely. Higher compression ratios mean higher temperatures, which means a bigger temperature. Difference between the hot source and the cold sink, which means, and here's Carnot's ghost again, better theoretical efficiency. You can see this playing out in modern engineering. A typical gasoline engine has a compression ratio of maybe 10 to 1. A diesel engine might run at 20 to 1 or even higher. And that difference, which sounds like just a number, translates directly into fuel savings, into miles per gallon, into how much carbon dioxide goes into the atmosphere per kilometer driven. Thermodynamics isn't abstract when you frame it that way. It's the reason a diesel truck can haul 40 tons of freight across a continent on less fuel per ton mile than almost any other form of land transport. Now, there's another cycle worth mentioning here, because it takes us from roads and railways into the sky, and it shows just how versatile these thermodynamic ideas are. The Brayton cycle, named after George Brayton, an American engineer who built an early constant pressure engine in the 1870s, is the cycle that describes how gas turbines and jet engines work. The idea is beautifully simple in principle. You take in air, compress it, add heat by burning fuel in the compressed air, and then let the hot gas expand through a turbine that extracts work. The exhaust comes out the back, and in a jet engine, that exhaust provides thrust. In a power plant gas turbine, the expanding gas spins the turbine, which turns a generator. Same thermodynamic cycle, different applications. And the efficiency of the Brayton cycle depends on, you guessed it, the pressure ratio and the temperature difference. Modern jet engines operate with turbine inlet temperatures that can exceed 1,500 degrees Celsius, and achieving those temperatures without melting the turbine blades is one of the great materials engineering challenges of our time. The blades in a modern jet engine are single crystal nickel superalloys with internal cooling channels and thermal barrier coatings, and they operate in gas that's actually hotter than the melting point of the metal itself. They survive because of that internal cooling. Cool air bled from the compressor flows through tiny passages inside the blade, keeping the metal just below its limits. It's thermodynamics and materials science and fluid dynamics all working together at the edge of what's physically possible. And this brings us to something important about how thermodynamics matured in the 20th century. The basic laws were in place by the early 1900s. The zeroth, first, second, and third laws, that whole framework we've been building, it was essentially complete. But what happened next was that engineers and physicists started applying those laws to increasingly complex and sophisticated systems, pushing the boundaries of efficiency, miniaturization, and scale. The 20th century wasn't really about discovering new laws of thermodynamics. It was about learning to use the existing laws with extraordinary precision and creativity. Take refrigeration, for instance. We've been talking mostly about heat engines, devices that convert heat into work. But a refrigerator is a heat engine running in reverse. Instead of letting heat flow from hot to cold and extracting work along the way, you put work in to pump heat from cold to hot. You're moving heat in the direction it doesn't naturally want to go, and the second law says you can do that, but it'll cost you. The coefficient of performance of a refrigerator, which is the ratio of heat removed to work input, is bounded by thermodynamic limits that are basically the Carnot efficiency flipped upside down. And the development of practical refrigeration in the late 19th and early 20th centuries transformed human civilization in ways that are easy to overlook. Before mechanical refrigeration, food preservation meant salting, smoking, drying, or using natural ice. The ability to keep things cold on demand changed agriculture, changed medicine, changed where people could live and what they could eat. Carl von Linde, the same professor who taught Rudolf Diesel thermodynamics in Munich, was one of the pioneers of industrial refrigeration. He developed ammonia compression refrigerators in the 1870s and 1880s that made large-scale cold storage practical for the first time. There's a lovely symmetry there. The same intellectual tradition, producing both better engines and better refrigerators, because they're really the same thermodynamic problem viewed from opposite directions. And speaking of viewing things from opposite directions, let's talk about something that connects back to a thread we left dangling earlier: the connection between entropy and information. Remember when we talked about Boltzmann's statistical interpretation of entropy, how it's related to the number of microstates consistent with a given macrostate, and I mentioned that this idea would eventually connect to information theory? Well, this is where that thread picks up, and it involves one of the most quietly brilliant people of the 20th century, Claude Shannon. Shannon was working at Bell Labs in the 1940s, and his problem had nothing to do with steam engines or heat. He was trying to figure out the fundamental limits of communication, how much information you can send through a noisy telephone line or radio channel. And in his landmark 1948 paper, A Mathematical Theory of Communication, he defined a quantity that measures the uncertainty or information content of a message. He needed a name for this quantity, and the story, which may be slightly apocryphal but is too good not to tell, is that he asked John von Neumann what to call it. Von Neumann supposedly said, "Call it entropy." In the first place, the mathematical formula is the same as in statistical mechanics, and in the second place, nobody really understands entropy, so in a debate, you'll always have the advantage. Whether or not that conversation happened exactly that way, the mathematical parallel is real and deep. Shannon's entropy formula looks almost identical to Boltzmann's. Both are sums over possible states, weighted by probabilities, with a logarithm involved. And this isn't a coincidence. It reflects something profound about the nature of information and disorder. Think about it this way. When you say a system has high entropy in the thermodynamic sense, you're saying there are many possible microscopic arrangements that would look the same from the outside. You have very little information about which specific microstate the system is in. When Shannon says a message source has high entropy, he means the messages are unpredictable. Each new symbol carries a lot of information because you couldn't have guessed it in advance. In both cases, entropy measures your uncertainty, your lack of knowledge about the precise state of things. A perfectly ordered crystal at absolute zero has zero thermodynamic entropy. There's only one microstate. You know exactly what's going on. A completely predictable message has zero Shannon entropy. There's no surprise, no new information. This connection between thermodynamics and information theory has turned out to be far more than a cute analogy. It's led to real, practical insights. There's a famous thought experiment called Maxwell's Demon. James Clerk. Maxwell proposed it back in 1867, where an imaginary tiny creature sits at a trapdoor between two gas chambers and sorts fast molecules to one side and slow molecules to the other, apparently decreasing entropy without doing any work, which would violate the second law. For over a century, physicists argued about what was wrong with this scenario, and the resolution, worked out by Leo Szilard in 1929 and made rigorous by Rolf Landauer at IBM in 1961, comes down to information. The demon has to observe each molecule, store that information, and eventually erase it. Landauer showed that erasing one bit of information necessarily dissipates a minimum amount of energy as heat. Specifically, kT times the natural log of 2, where K is Boltzmann's constant and T is the temperature. That tiny amount of heat generation is enough to save the second law. The entropy decrease from sorting the molecules is exactly compensated by the entropy increase from the demon's information processing. Information isn't free. It has a thermodynamic cost. And this principle, Landauer's principle, has been experimentally verified. In 2012, a team in France actually measured the heat generated by erasing a single bit of information in a carefully controlled experiment, and the result matched Landauer's prediction. This has real consequences for the computers in your pocket and on your desk. Every time a computer erases or overwrites a bit of data, there's a minimum amount of heat that must be generated. Modern computers operate far above this theoretical minimum. The heat from your laptop is mostly due to electrical resistance and other practical losses, not Landauer's limit. But as circuits shrink and computing becomes more energy efficient, that fundamental thermodynamic floor gets closer and closer. Some researchers think about this when they imagine the ultimate limits of computation. How much calculation can you do with a given amount of energy? And the answer, ultimately, is set by thermodynamics. So here we are, in a world where the laws that Carnot and Clausius and Boltzmann laid down are woven into everything from the jet engine overhead, to the phone on your nightstand, to the data centers that power the internet. And there's one more enormous arena where thermodynamics plays a starring role, one that affects every person on the planet. And it's worth talking about slowly, because it might be the most consequential application of thermodynamics in human history: the Earth's energy balance, climate, the way our planet manages heat. And the beautiful thing is, you already have every tool you need to understand it. Everything we've been building, from Carnot's heat engines to Clausius's entropy to Boltzmann's statistical mechanics, it all converges here, on this pale blue dot spinning in space, absorbing sunlight and radiating heat into the void. So let's think about it simply. The Earth receives energy from the sun, mostly visible light, photons streaming across 93 million miles of vacuum. Some of that energy bounces right back off into space, reflected by clouds, ice, deserts. But a good portion of it gets absorbed by oceans, by land, by the atmosphere itself. And here's the thing: the Earth doesn't just keep accumulating that energy forever. If it did, the planet would heat up without limit, which obviously hasn't happened over 4.5 billion years. Instead, the Earth radiates energy back out into space, but it radiates it differently from how it received it. The incoming energy is mostly high-frequency visible light, because the sun's surface is about 5,700 Kelvin. The outgoing energy is mostly infrared radiation, lower frequency, longer wavelength, because the Earth's surface is only around 288 Kelvin, roughly 15 degrees Celsius on average. Now think about what that means in thermodynamic terms. The Earth is a system sitting between a hot reservoir, the sun, and a cold reservoir, the deep cold of outer space, which is about 2.7 Kelvin, barely above absolute zero, thanks to the cosmic microwave background. Energy flows in from the hot source, passes through the system, and flows out to the cold sink. That's a heat engine. The Earth is, in a very real thermodynamic sense, a heat engine. And like any heat engine, it's the temperature difference between the hot source and the cold sink that drives everything interesting. All the weather, all the ocean currents, all the convection in the atmosphere, all the evaporation and precipitation. Carnot would recognize this setup instantly. But here's where it gets really interesting, and where a concept from the 1860s becomes urgently relevant in the 21st century. The atmosphere isn't perfectly transparent to all wavelengths of radiation. Visible light from the sun passes through the atmosphere pretty easily. That's why you can see the sun, why daylight reaches the ground. But infrared radiation, the kind the warm Earth emits back upward, doesn't pass through as easily. Certain gases in the atmosphere, water vapor, carbon dioxide, methane, nitrous oxide, a few others, absorb infrared photons. They catch that outgoing heat and re-radiate it in all directions, including back down toward the surface. This is the greenhouse effect, and it's not some modern invention or controversial theory. It's straightforward thermodynamics, and it was first described quantitatively by a remarkable person most people have never heard of, Eunice Newton-Foote. In 1856, 3 years before Darwin published On the Origin of Species, 9 years before Clausius coined the word entropy, Foote conducted a simple but elegant experiment. She filled glass cylinders with different gases, placed them in sunlight, and measured how much each one heated up. She found that a cylinder filled with carbon dioxide got significantly hotter than one filled with ordinary air, and it stayed hot longer after being removed from sunlight. She presented her findings at the annual meeting of the American Association for the Advancement of Science, though her paper was actually read aloud by a male colleague, Joseph Henry, because of the conventions of the time. Her conclusion was direct and prescient. She noted that an atmosphere rich in carbon dioxide would give the Earth a higher temperature. That's 1856. Think about that. 3 years later, the Irish physicist John Tyndall conducted more detailed laboratory experiments on the absorption of infrared radiation by various gases. Tyndall had more sophisticated equipment and was able to show precisely which gases were strong absorbers of radiant heat. Water vapor turned out to be the most powerful greenhouse gas by volume. But carbon dioxide was also significant. Tyndall understood the implication immediately. These gases act like a partial blanket around the Earth, trapping some of the outgoing heat that would otherwise escape to space. Without any greenhouse effect at all, the Earth's average surface temperature would be something like -18 Celsius, well below freezing everywhere on average. The natural greenhouse effect, mostly from water vapor and carbon dioxide, that's been in the atmosphere for eons, warms the planet by roughly 33 degrees Celsius, making it habitable. So the greenhouse effect itself isn't the problem. It's what makes life possible. The question, the thermodynamic question, is what happens when you change the composition of that atmospheric blanket. And this is where a Swedish chemist named Svante Arrhenius enters the story. In 1896, Arrhenius sat down and did an extraordinary calculation. He wanted to understand what had caused the ice ages, what could make the Earth cool enough to cover huge swaths of the northern hemisphere in glaciers. He suspected changes in atmospheric carbon dioxide might be responsible. So he calculated by hand, using data from Tyndall and from the astronomer Samuel Langley's measurements of lunar infrared radiation, how the Earth's temperature would change if you doubled or halved the concentration of carbon dioxide in the atmosphere. It took him over a year of painstaking arithmetic, thousands of calculations done with pencil and paper, working through the radiation balance for different latitudes and seasons. And his result was remarkably close to modern estimates. He found that doubling atmospheric carbon dioxide would raise the global average temperature by about 5 to 6 degrees Celsius. Modern climate models, running on supercomputers with vastly more data and physics, estimate the number, called climate sensitivity, at somewhere between 2.5 and 4 degrees Celsius for a doubling of CO2. Arrhenius was in the right ballpark with nothing but a pencil. And here's a curious footnote. Arrhenius, living in chilly Sweden, actually thought a warmer world might be pleasant. He didn't foresee the scale of fossil fuel burning that the 20th century would bring, and he imagined the warming would take thousands of years. He was wrong about the timeline, but his physics was sound. So what's actually happening? Thermodynamically? You can think of it this way. The Earth's energy budget has to balance. Energy in from the sun has to equal energy out radiated to space, at least on average over time. If you add more greenhouse gases to the atmosphere, you're making it harder for infrared radiation to escape. It's like adding another layer to a blanket. The immediate effect is that less energy gets out than is coming in. The system is out of equilibrium. There's a net energy imbalance. And what does a system do when it's absorbing more energy than it's releasing? It warms up. The temperature rises, and as the temperature rises, the Earth radiates more intensely. Remember, the Stefan Boltzmann law says radiated power goes as the fourth power of temperature. So the planet warms until it's radiating enough to restore the balance, but at a higher temperature than before. This is pure thermodynamics. It's the same logic as asking why a pot of water on a stove reaches a steady temperature. The rate of heat loss increases with temperature until it matches the rate of heat input. The Earth is doing the same thing, just on a planetary scale with a more complicated set of feedbacks. And those feedbacks, this is where the complexity explodes. Warming melts ice, which exposes darker ocean or land underneath, which absorbs more sunlight instead of reflecting it, which causes more warming. That's a positive feedback loop. Warmer air holds more water vapor. The Clausius-Clapeyron relation, named partly for our old friend Rudolf Clausius, describes this precisely. And since water vapor is itself a greenhouse gas, more water vapor means more warming, which means more water vapor. Another positive feedback. On the other hand, more water vapor might mean more clouds, and clouds reflect sunlight back to space, which is a negative feedback, a cooling effect. The net result of all these interacting feedbacks is what makes climate prediction so challenging. And it's why climate scientists build enormously complex models. But the underlying thermodynamics, the energy balance, the radiation physics, the second law driving heat from warm to cold, that part is settled. It's been settled since Fourier first thought about planetary temperatures in the 1820s, since Foote and Tyndall did their experiments in the 1850s, since Arrhenius did his calculations in the 1890s. What's remarkable is how directly this connects to everything we've talked about. The efficiency limits Carnot discovered tell you something about how much useful work you can extract from temperature differences in the atmosphere. And those temperature differences drive hurricanes, which are literally heat engines, pulling energy from warm ocean surfaces and exhausting it high in the cold upper atmosphere. The entropy that Clausius defined governs the irreversible mixing of greenhouse gases once they're released. Boltzmann's statistical framework underpins the quantum mechanics of how gas molecules absorb and re-emit infrared photons. Each molecule has specific vibrational modes, specific energy levels, and it's the transitions between those levels that determine which wavelengths of infrared light get absorbed. Carbon dioxide, for instance, has a strong absorption band around 15 micrometers wavelength, right in the middle of the range where Earth emits most of its thermal radiation. That's not a coincidence or bad luck. It's molecular physics, which is statistical thermodynamics at the quantum level. And here's something that ties it all the way back to the very beginning of our story, back to those early steam engines. The reason we're adding carbon dioxide to the atmosphere in the first place is because we're burning fossil fuels, coal, oil, natural gas, to power heat engines, cars, power plants, jet turbines, industrial furnaces. We are running Carnot cycles, Rankine cycles, Otto cycles, diesel cycles, Brayton cycles, all the thermodynamic cycles we talked about, on a massive civilization-wide scale. And every single one of them, by the second law, must reject waste heat. Every single one of them produces exhaust. And when the fuel is carbon-based, that exhaust includes carbon dioxide. The very efficiency limits that Carnot identified in 1824 mean that we can never convert all the chemical energy in fossil fuels into useful work. Some energy must always be wasted as heat, and the combustion products must go somewhere. For 2 centuries, they've been going into the atmosphere. So thermodynamics giveth, and thermodynamics taketh away. It gave us the Industrial Revolution, modern transportation, electricity, computing. And the same laws, the same inescapable, universal laws, Now describe the planetary consequences of all that activity. There's a deep, poetic symmetry there, if you think about it. Carnot was trying to understand the limits of steam engines in post-Napoleonic France, and the framework he built now helps us understand why the planet is warming and what the physical constraints on our response might be. Because those constraints are real. You can't just wish away the second law. If you want to remove carbon dioxide from the atmosphere, you have to do work, thermodynamic work, to separate it from the other gases and concentrate it. That work requires energy, and if that energy comes from burning more fossil fuels, you haven't gained much. The minimum energy required to separate CO2 from air is set by thermodynamics. It's related to the entropy of mixing, and at current atmospheric concentrations of about 420 parts per million, it's not trivial. Engineers working on direct air capture technology are essentially fighting against entropy, trying to unmix a very dilute gas from a vast ocean of air. And every step of that process is governed by the same principles Clausius and Boltzmann laid down. This is also why renewable energy sources matter from a thermodynamic perspective. Solar panels and wind turbines don't burn anything. They intercept energy flows that are already happening. Sunlight hitting the ground, wind driven by differential solar heating, and convert some of that energy into electricity without adding new carbon dioxide to the atmosphere. They're still subject to efficiency limits, of course. A solar cell has a theoretical maximum efficiency called the Shockley-Queisser limit, about 33% for a single junction cell, and that limit comes from, you guessed it, thermodynamics and quantum mechanics working together. But the crucial difference is that the waste heat from a solar panel was going to become heat anyway when the sunlight hit the ground. You're not adding new energy to the system the way burning fossil fuels does. And all of this connects to something even larger, something that takes us beyond engineering and into the deepest questions about the nature of time itself. Because here's something that might keep you up at night, or, well, gently lull you to sleep while your mind chews on it. Almost every fundamental law of physics works perfectly well in both directions of time. Newton's laws, Maxwell's equations, even quantum mechanics at its most basic level. If you filmed a process governed by those laws and played the film backward, the reversed version would also be a perfectly valid physical process. A ball thrown upward and coming back down looks just as reasonable in reverse. Two billiard balls colliding and bouncing apart. Reverse the film, and they collide and bounce apart in a way that obeys all the same equations. Time, at the level of fundamental physics, doesn't seem to have a preferred direction. And yet, you know from every moment of your lived experience, that time absolutely does have a direction. Ice melts in warm water. It never spontaneously unmelts. A cup falls off a table and shatters. The shards never leap back up and reassemble themselves into a cup. You get older. Smoke disperses. Perfume spreads through a room. These things only happen one way. There is an arrow to time, and you feel it in your bones. So where does that arrow come from? If the microscopic laws of physics are time-symmetric, why is the macroscopic world so stubbornly asymmetric? This was one of the great puzzles of 19th century physics, and the answer, or at least the best answer we have, comes directly from the work we've been talking about all night. It comes from entropy. From Boltzmann. Think back to what Boltzmann showed us. Entropy is about the number of microstates consistent with a given macrostate. A low entropy state, like all the gas molecules crammed into one corner of a room, has very few microstates that could produce it. A high entropy state, gas spread evenly throughout the room, has an astronomically larger number of microstates. So if you start in a low entropy state and let the system evolve according to the laws of physics, it's overwhelmingly likely to move toward higher entropy, simply because there are so many more ways to be high entropy than low entropy. It's not that the laws of physics forbid the gas from spontaneously rushing back into the corner. It's that the probability of that happening is so vanishingly small. We're talking numbers like 1 divided by 10 raised to the power of 10 raised to the power of 23. That you could wait for the entire age of the universe multiplied by itself 1 billion times and still never expect to see it. That's the arrow of time. It's statistical. It's not baked into the fundamental equations. It emerges from the sheer mathematics of large numbers. And that's both deeply satisfying and a little unsettling, because it means the arrow of time is in some sense not fundamental. It's emergent. It arises because we live in a universe that, for reasons we don't fully understand, started in a state of remarkably low entropy. And that's worth sitting with for a moment. The fact that your coffee cools down, that you age, that yesterday is different from tomorrow. All of that traces back to the initial conditions of the universe. The Big Bang, roughly 13.8 billion years ago, produced a cosmos in an extraordinarily low entropy state. Matter was distributed with astonishing uniformity. The cosmic microwave background radiation, that faint afterglow of the early universe, is uniform to about 1 part in 100,000. And from that smooth, hot, dense beginning, gravity has been pulling matter together into clumps, stars, galaxies, planets, while radiation spreads out and entropy climbs. The entire history of the universe, in a thermodynamic sense, is the story of entropy increasing from that improbable starting point. This idea was explored beautifully by a number of physicists, but one who put it most vividly was Arthur Eddington, the British astrophysicist, who in 1927 coined the phrase, the arrow of time. Eddington wrote that the second law of thermodynamics holds, he believed, the supreme position among the laws of nature. He said, and I'm paraphrasing slightly, that if your theory is found to be against the second law of thermodynamics, there is nothing for it but to collapse in deepest humiliation. He took it that seriously. And he was right too, because the second law isn't just about engines and refrigerators. It's about the fundamental directionality of everything that happens. Now, here's where it gets cosmologically interesting. If entropy has been increasing since the Big Bang, and if it continues to increase, where does that lead? Well, in the late 19th century, physicists began contemplating what they called the heat death of the universe. The idea is straightforward, if melancholy. If entropy always increases, then eventually the universe will reach a state of maximum entropy, thermodynamic equilibrium. Every temperature gradient will have smoothed out. Every star will have burned through its fuel. Every black hole will have evaporated through Hawking radiation, a process that itself is deeply thermodynamic. And what's left is a vast, cold, uniform expanse where nothing interesting can ever happen again, because there are no gradients left to drive any process. No hot and cold, no high and low, just equilibrium. Forever. Lord Kelvin was one of the first to articulate this vision back in the 1850s, and it genuinely troubled people. It still troubles people if they think about it long enough. The idea that the universe has an expiration date, not a dramatic explosion, but a slow, quiet fade into absolute uniformity, is one of the most profound consequences of thermodynamics. It's the second law, extrapolated to the largest possible scale. But here's the thing that's easy to miss in all that cosmic gloom. We're not at heat death. We're not even close. we live in the interesting part, the long, slow, glorious middle stretch where entropy is increasing. Yes, but where that very increase is what makes complexity possible. Think about that. It sounds paradoxical, doesn't it? Entropy is supposed to be about disorder, about things falling apart. How can increasing entropy create complexity? The answer is that local decreases in entropy are not only permitted by the second law, they're expected, as long as they're paid for by even larger increases elsewhere. And that's exactly what life does. You, right now, lying there listening to this, are a spectacularly low entropy structure. Your body maintains precise temperature gradients, chemical gradients, electrical gradients. Your cells are organized with extraordinary specificity, proteins folded into exact shapes, DNA encoding billions of base pairs in precise sequence. All of that order, all of that low entropy, is maintained by a continuous flow of energy. You eat food, low entropy, organized chemical energy, and you radiate waste heat, high entropy thermal energy, into your surroundings. You are, thermodynamically speaking, a dissipative structure. You maintain your internal order by exporting entropy to the environment. And the energy that drives the whole chain, the sunlight that grew the plants that fed the animals that became your dinner, that energy ultimately comes from the sun, which is a hot object radiating into the cold of space, and that temperature difference is what makes everything go. Erwin Schrödinger, the quantum mechanics pioneer, explored this beautifully in a little book called What is Life? Published in 1944. He argued that living organisms feed on what he called negative entropy, or negentropy, drawing order from their environment to maintain their own internal organization. It was a remarkable insight for its time, and it anticipated much of what we now understand about the thermodynamics of biological systems. Life doesn't violate the second law. It surfs on it. It rides the wave of entropy increase, carving out temporary pockets of order along the way. And here's what's really beautiful about that. The same framework, the same thermodynamic principles that Sadi Carnot developed to understand steam engines in 1824, that Clausius formalized, that Boltzmann grounded in statistics, that Nernst extended to absolute zero. That same framework explains why you're alive, why anything is alive, why stars shine and rivers flow and hurricanes spin and crystals grow. It's all thermodynamics. It's all about energy flowing from concentrated forms to dispersed forms and the incredible variety of things that can happen along the way. Let's come back to Earth for a moment, because there's something poetic about where this whole journey has taken us. We started with steam engines, with Newcomen's clunky, inefficient atmospheric engine pumping water out of coal mines in early 18th century England. That engine existed because miners needed to dig deeper to get more coal. The coal was burned to power the engine that dug up more coal. And the coal was burned in other engines to drive the Industrial Revolution, factories, railways, steamships that transformed human civilization. And all of that burning released carbon dioxide into the atmosphere, molecule by molecule, year by year, decade by decade, until the concentration climbed from about 280 parts per million before the Industrial Revolution to over 420 today. And that additional carbon dioxide, through the greenhouse effect that Eunice Foote first noticed and Arrhenius first calculated, is warming the planet. So the story of thermodynamics is also the story of how we got into our current climate predicament. The very science that enabled the Industrial Revolution, the understanding of heat, work, and efficiency, is also the science that explains why that revolution's byproducts are changing Earth's energy balance. There's a deep irony there, or maybe it's not irony at all. Maybe it's just consequence. The second law doesn't care about irony. It just is. But that same science also points toward solutions. Better heat engines that extract more work from less fuel. Solar cells that harvest energy without combustion. Heat pumps that move thermal energy with remarkable efficiency. 3 or 4 units of heat delivered for every unit of electricity consumed, which seems like magic until you realize it's just the second law working in your favor for once. Engineers today are using every principle we've talked about tonight: Carnot efficiency, entropy minimization, phase transitions, statistical mechanics, to design systems that can sustain human civilization without destabilizing the climate. The tools are thermodynamic. They always have been. And maybe that's the most comforting thought to drift off with. Thermodynamics can sound intimidating. All those laws, all that entropy, the specter of heat death. But at its heart, it's the most practical, most grounded, most deeply connected to everyday life branch of physics there is. Every time you feel warmth from a cup of tea, you're experiencing the 0th law. Every time you pay an electricity bill, you're reckoning with the first. Every time you notice that your coffee got cold, but never saw it spontaneously get hot, you're witnessing the second. And every time you hear about scientists pushing toward colder and colder temperatures, approaching, but never quite reaching absolute zero, that's the third. These laws were figured out by real people, brilliant, stubborn, sometimes tragic people, over the course of about 200 years. Carnot, who died young and whose work was almost lost. Joule, the brewer's son with his thermometers and paddle wheels. Clausius, careful and precise. Boltzmann, visionary and tormented, who saw deeper into the nature of matter than almost anyone of his era, and paid a terrible price for being ahead of his time. Nernst, competitive and clever, all of them wrestling with the same basic questions. What is heat? What is energy? Why do things change? And what are the limits of what we can do? Those questions turned out to be connected to everything. To the engines that power civilization, to the air you breathe, to the climate that sustains life, to the arrow of time that carries you from one moment to the next, to the very fact that you exist at all as an ordered structure in a universe trending toward disorder. Thermodynamics is the thread that runs through all of it, quiet and constant, like a low hum beneath everything. So let that thought settle. Let it be a gentle, steady thing in the back of your mind as you drift. The universe is winding down, slowly, over time scales so vast they make human history look like the blink of an eye. But right now, in this moment, energy is flowing. Gradients are driving beautiful complexity into existence, and you, a temporary, magnificent pocket of low entropy, are here to wonder about it all. That's not a bad place to be. Not a bad place at all. Let your breathing slow. Let the ideas soften and blur at the edges. They'll be there in the morning if you want them. For now, just rest.